Students, we were discussing the LR circuit and we have completed the derivation for the LR circuit. Okay. Now students, the equations that we require in order to draw the conclusion that we can see from the derivation, let us write those equations which we need. Okay. So today's topic is LR circuit. Just write the equations once again. I'm writing it. That is for the applied alternating voltage, which is equal to V naught sine omega t. This is your equation number 1. Okay, this we have to take, and the third equation, students, you can see, that is I equals to I naught sine omega t minus theta, which is equal to V naught by Z sine omega t minus theta. This was your equation number 3, and we have to consider these two equations in order to draw the conclusion. Okay. So from this, students, equation number 1 and 3, we can conclude that the current is lagging behind the applied voltage by a phase angle theta. Have you seen that there is a phase angle between these two equations, the theta, and it is given by tan theta. I am writing it here. Tan theta equals to sin theta by cos theta. In the maths class, hope you have learned. Okay, and which is equal to, just recall the value of sin theta that we have written in the derivation. The value of sin theta and the cos theta in the derivation that we have assumed in order to reduce our derivation, that you have to recall. And now I am going to put those values here, which is equal to omega L by Z into cos theta's value was R by Z. So since it is in the denominator, it will get reversed. It will be Z by R. Clear? So Z and Z will get cancelled and you will be left with only omega L by R. Understood? Okay. So what will be your value of theta? Therefore, theta will be your tan inverse omega L by R. This is also you have learned in the maths classes. Alright. Okay. So this is basically the phase relation that you can draw from the two equations. Okay. This first one and the second one. Alright. So students, we know that in a pure resistive circuit, V and I, your voltage part and your current part, are in the same phase. That means when they are in the same phase in the case of the purely resistive circuit, so your theta, that is the phase angle, phase difference, will be 0, isn't it? I am writing it here. In resistive circuit, okay, your theta, that is your phase difference, is 0 because your voltage and your current, two parts, are in the same phase. But in the case of purely inductive circuit, what happens? Your I part always lags behind V by this theta. I have shown you all. Okay. So what will be the value of that theta in the case of this purely inductive circuit? Its value will be, I am writing it here, in purely inductive circuit, your theta will be equals to 90 degree, isn't it? So in an LR circuit, I should lag behind V by 90 degree. Okay. So in another way, how can I write it? Okay, in this mathematical form also, students, I can express these things in this form. Alright. So okay, just let us represent it in the graphical manner. Okay. This is your VR, this is your VL, this is I, this is V, and this is your theta. Okay. Okay. So first conclusion, we have seen what we can draw from this derivation. Now let us move to the second conclusion that we can draw from these two equations, equation number 1 and equation number 3. Alright. So your second conclusion can be like this, that in this particular circuit the Z part plays the same role as the R in the case of the purely resistive circuit. Okay, so Z is known as the impedance of an AC circuit. Z is called as the impedance in an AC circuit. Circuit I'm writing in short. Clear? So what will be the value of impedance? Just recall the derivation. Z's value was R square plus omega L whole square. Just recall the derivation. Okay. So instead of writing this omega L, I can write it in this way. Root R square plus XL whole square. Isn't it? I can write it, the omega L, I can write it in this XL form. Clear? Where this XL means omega L, which is your inductive reactance. Inductive reactance. Okay, this XL part is called as the inductive reactance. Okay, so if the question comes like this, what do you mean by the impedance in the circuit? So you can write it in this way, that impedance in this LR circuit is the effective resistance of the circuit arising from the combined effects of both the ohmic resistance and the inductive reactance. That means basically what you can say, that this is the combination of the two types of resistance that we have seen while drawing the circuit diagram. What are the two types of combination? One is the ohmic resistance, that is your R part, and your inductive reactance, that is your omega L part. That means it's the combination of both of this reactance and the resistance. Clear? Okay. So nearly we have completed the two conclusions. Okay. Now students, one thing that one short question can come, that the impedance triangle is what? Okay, and how to represent it. So students, I am putting the impedance triangle, how you can draw impedance triangle. Impedance triangle look like this. This you have to write it, this part as your, that means your vertical y part should be written as omega L. This x-axis part or the horizontal part is your R resistance, and this is your phase difference, and this is your Z part. This is your impedance triangle. Okay. Okay. If the question comes like this, that what does the impedance triangle looks like, or how does the impedance triangle looks like, you will put this diagram.